We are here to talk about the cloud machine learning offerings from the beginner's perspective. All right, quick outline. We're going to introduce ourselves, kind of set the stage a little bit, set some framing and some expectations. Then we're going to discuss the problem that we're going to use as our example for the rest of this talk, which is who wins at DotA 2, a video game. And we'll explain a little bit more about DotA 2 for those who aren't familiar with it momentarily. We're going to run through that, solving that problem using Jupyter on the cloud platforms. And then we're going to talk through the differentiators for each of those cloud platforms and kind of come up with our conclusions. I'll go ahead and just give the big takeaway, give it away here at the beginning. The major offerings each have similar capabilities. The differentiators should not dictate your choice of cloud provider. Use where you are, if possible. We'll talk more about that at the end, though, but that's setting some expectations right now. So who are we? My name is Robert Herbig. Also on the line is my colleague, Jordan Thayer.
Hello.
All right. We work at SEP. We are AI practice leads. SEP is a small software consultancy, and I will mention no more about that, so we focus on this content. So we describe ourselves as machine learning experts, as the practice leads at SEP. However, we are still beginners in terms of cloud offerings. We've used them to some extent. We might have used them on other projects for web apps and that kind of thing. But mixing this intersection of ML and cloud is relatively new to us. So that's where we are. We expect most people in the audience are going to be in these three quadrants: beginner in both, in the corner, expert cloud beginner ML, or beginner cloud expert ML. If you're so that's sort of where we're aiming. Where we're going to try. We're going to go through some amount of description of what ML is, some amount of information on the cloud, sort of a breadth first approach, and then talk about the three major providers. AWS's SageMaker is their ML offering. We're going to talk about Microsoft's Azure offering, and then Google's cloud AI platform.
But to start things off, we'll dig into sort of what machine learning is. If you haven't heard of machine learning before, welcome back. It's good that you've woken from your coma. So it's sort of difficult these days to not have heard it in some context, either in business magazines or in technical circles. And I think one problem that we all recognize as a machine learning problem is shown here in the upper right. What we've got is some slides of various kinds of tissue, and we're trying to identify whether or not the tissue is a malignant tumor or sort of a benign tumor or healthy tissue. But there are other kinds of things that fall under the umbrella of machine learning. So for example, if you've got a cart with a stick balanced on it and you want to keep that stick balanced by moving the cart left and right, that's what's called a reinforcement learning problem. And that's a machine learning problem too. If you've got a signal and you want to pick out certain regimes in that signal, but you don't really know what a regime looks like, that's a learning problem as well. Signal identification can be solved with unsupervised learning. So we're going to focus on a problem like the upper right here today, but all of the platforms that we're going to talk about, and many of the platforms that we don't, when they say that they support machine learning, they mean a much larger thing than what we're going to focus on here. We're going to focus on that supervised case, but they support reinforcement and unsupervised learning techniques as well. So to just drill down a little bit more on the case that we're looking at today, what we're going to look at doing is taking labeled examples of things. So this particular slide shows a cancerous tumor. This one shows a benign tumor. This one shows healthy cells. And we're going to try and teach the machine how to identify that sort of thing from data. We're not going to be doing it on anything quite so lofty and useful. We're just going to use a toy problem.
Now, in the interest of focusing our attention on that intersection between cloud and ML, there's a couple things we're not going to be covering, and I want to call those out very specifically. Infrastructure as code is a really good idea in general, but it's not critical for this learning setting that we're in right now about this intersection of the two concepts. Likewise, version control. Most of the models that we're going to talk about here can be saved in an artifact repository in some way. All this custom code could be stored in a version control system and then pulled into the cloud or used in some way like that. Again, we're not going to focus on that, so we focus on this much smaller subset of features. So the problem that we want to talk about is who wins Dota 2, Dota 2 being a video game. Quick overview of Dota 2. It is a match-based system where there are 2 teams. Each team has 5 players. Each player controls 1 hero. The 2 teams have a base, each have a base, and the goal is to destroy your opponent's base before yours is destroyed. Pretty straightforward at that really high level. There are a very large number of heroes to choose from. You can see, and I think this is actually an older image. There's more heroes than this, but each of those pictures is 1 hero that you can choose. And we're going to try and predict from which heroes are on each team, which team we think will win.
So if you've done any machine learning before or read about it, you know that the first thing you really need to do to dig in is to get a data set. So what we need is a recording of a bunch of matches of Dota, who won, who lost, and who was playing whom. We could build some tooling to scrape that from the internet because there's an API and it's published, but mercifully someone has gone to that effort for us. So what you're looking at here is a web page from the University of California, Irvine. They maintain a large number of data sets used in different academic papers. So if someone's written a paper on machine learning or done a project on machine learning at the university, that data set is stored and curated by the U. So if you're looking to get some problems to toy around with and get started in machine learning, this is a collection of those things that's extremely useful. And we'll have some links afterwards if you want to follow up on that. So the data set that we're using today, we pulled from here. And it looks like this. So it's a big CSV file. You can ingest it in your favorite spreadsheet program and take a look at it. I know that resolution-wise, no one can probably read this, so let's drill in a little bit. The data give us the following thing. So in the far left, we've got the team 1. That's either going to be -1 or 1 for team A wins, team B wins. It's a zero-sum game. Then there's some information about where the game was played. The cluster ID relates to geographic region roughly. Game mode and game type are going to be important for us because we're not just trying to predict who wins and who loses in Dota 2. We've actually narrowed our hypothesis down a little bit. We assume that team composition is indicative of wins and losses as long as you control for the relative skill of the players. Since we don't have a good insight into relative player skill in the data set that we've got, what we do instead is we rely on the ranked matches that Dota 2 has. So there's a matchmaking algorithm that tries to pair teams of comparable skill, and we lean into that. The rest of the information is just team composition. So you see the names of different heroes and a bunch of zeros. There are also some 1s and -1s that relates exactly to the team won, team lost. Which team were they playing for? So what we're gonna try to do is we're gonna try to predict this, the left-hand column, wins and losses, from these being the rest of the data. To use the more common terms for machine learning, what we have are labels, who won and who lost, and we'd like to predict the labels from the features, the rest of the information that's present in the data set.
All right, so how do we do that? Let's give a quick overview of machine learning. And again, since this is focused on the intersection of the 2 technologies, we're going to go kind of breadth first and just lightly talk about machine learning itself. Machine learning starts with training. So we have some amount of data that Jordan just described to us and went over. We're going to call that training data. What we do is that training data consists of data points. So this is rows in the CSV, for example, which have a label and the features. So we have a known label for each of those rows in the training set. We're going to feed all that data into the machine learning algorithm, and we're going to get out the other side a model. With that model, we can then take unlabeled features and we can hand them to the model and say, will you please predict what label you think these features should have? It will then output the labels. The way we evaluate the model and know if it's doing anything, if it's any good or not, is we take our whole input data set and we actually split it into 2 pieces. One is for training and one is for testing. So we started with the whole CSV. We would split that in some way, and we'll see a little bit more of that later. So we can then hide the labels from the testing set, feed those features in, and we can then check, do the labels that were output by the model match the labels that we hid from the model, from the testing set. A different way to visualize this is with a pipeline approach. And I believe you'll hear several of the future presenters in the next 2 days talk about this same pipeline idea. It's pretty common in ML. You start with some data source, then the next gray box, you've got some sort of data ingestion, preparation, validation, preparation, the cleansing steps, you might hear about that, to get the data into a machinable format. Then you've got machine learning and evaluation, two things we just talked about, and then deployment. We'll go into a little bit more of deployment later as we go.
So the first thing we're going to look at is exploring your machine learning problem using Jupyter notebooks. And you might ask, well, what is Jupyter and why are you going to cover that? Well, so Jupyter is a fairly widely adopted tool at this point for doing data science and machine learning projects and exploration. It's really well suited to early prototyping for the reasons that we'll explain right now. So on the right, what we see is an example Jupyter notebook. This one's in R. And you see that it's got sort of an intermixing of rich text, source code, and visualizations. Idiomatically, it sort of works like a lab journal, if you want to think back to high school chemistry or physics classes. So the notion is that you do some work, you write down what it is you intend to do or what you intend to explore, you evaluate those outcomes, you put your graphs of performance right there in the same channel so that you have sort of a narrative of, this is what I was doing, this is what I was thinking about, this is what I was trying to achieve. And for initial steps, that's really, really nice to have all of that stuff right there in front of you explaining, well, this is why I did this thing. This is what I had hoped it was going to be doing. Jupyter's really great at that. Where it starts to have some problems is when you want to move into productizing or productionizing your system. It fights against certain best practices with respect to development. Version control is possible, but more difficult. Using things like linters is also going to be more difficult because it wraps the source code in some other structures. Another reason that we're going to look at Jupyter is not only is it sort of great for these initial explorations, but pretty much, I want to say all, but certainly all of the platforms that we talk about today support Jupyter notebooks as a way of interacting with machine learning in the cloud. So let's dig in there. We'll see first how Jupyter notebooks work on AWS, and then Rob will talk about how that process differs for Google Cloud and Microsoft Azure. So we're going to go through the use of Jupyter notebooks by looking at the various pipeline stages, and we'll start with data ingestion. The first thing that we need to do to get data up into a Jupyter notebook is actually construct an instance of a notebook for ourselves. So here you see my dashboard for Amazon Web Services and SageMaker in particular. And the first thing I'm going to do is I'm going to click the orange button right underneath this red arrow, give myself a Jupyter notebook instance. So I've spun up an instance. I've called it DotA2 classifier. I'm going to kick off, I'm going to start up that instance. And the first thing it's going to ask me is, well, what sort of a notebook do you want to have? And for the rest of the examples here, we're going to use Python notebooks because that's what we use in our day-to-day and what we're most familiar with. Once I've got the notebook style selected, the next thing I'm going to do is I'm going to click this, this upload button that's pointed to by the red arrow. I'm going to put my data files up into the notebook so that I can use them. It's as simple as dumping the CSV files that we got from the UC Irvine repository. I think those were in a zip file. So we just say, hey, upload these so that I can look at them and use them. Once we've got the data uploaded, we need to do some validation and some preparation so that we can use it for machine learning. So what that's going to look like is writing Python for the Jupyter notebook. We're just going to do some coding. So the first thing I do is import some libraries that are going to help me manipulate CSV files and give me some tooling to explore the data from a statistical standpoint, looking at sort of what's the average hero composition, what's the most frequently selected hero, that sort of thing. So what I'm going to do for data cleansing is I'm going to write this helper function which filters out games that I don't care about. You might recall previously we said that we wanted to see if we could predict wins and losses based on team composition, and we restricted ourselves to teams of relatively similar skill. The way we're going to do that is by filtering out certain game modes. So we're only going to care about ranked matches. And that's what that filter game modes function here on the left is doing. If you look at the right, I've got sort of a line of Python, but the arrows split it into different sections. So we start by loading the CSV file in, then we prepare the data by passing the filter over it and discarding elements that we don't want to learn against or don't want to evaluate against because they're not meaningful to us. And then finally, we spin up a learner. We say, well, I'm going to import a decision tree classifier from scikit-learn. I'm going to feed it some data to train the decision tree, and then I'm going to evaluate it, much in the way Rob showed with our meat grinder caricature before. So part of that data cleansing process, though, is inspecting the file just to make sure that I actually uploaded what I meant to upload and that I have about as many rows as I might expect to see. So here you see some of the niceties of Jupyter shown off, right? I've got some source code here in block 4. I'm doing some pretty printing of the CSV file, and then I get that pretty printed output right underneath there, so I can actually, get a record of what the console log would have been. I could have also done some visualizations here if I wanted to draw some histograms of character selection frequencies, things like that. Now that I've made sure that the data is what I want, we move on to machine learning and evaluation. We already showed a little bit of the training. The last step is doing the evaluation. So what we're going to do is ask the train learner to predict the new labels from a reserved portion of the data, the testing set that Rob talked about earlier. And we're going to compare what we predicted to what actually came out. And you see the final lines on this image are that we got roughly 5,400 correct, about 4,800, 4,900 wrong, and that's an overall accuracy of 52, 53%. So we're doing a little bit better than a coin flip. It's not necessarily what you want to see for your first foray, but what that tells you is, well, it's not entirely hopeless. I haven't done a bunch of advanced things that I could. For example, we're not considering categories of heroes, right? There are things like healers and crowd control, DPS characters, and we could sort of enrich our data set with our knowledge of the game. But just from a basic starting point, we've got a sense that, well, this is how far we have to go to get to a useful predictor. And that's really what the first step with Jupyter is all about, is figuring out sort of what the lay of the land is, how much elbow grease you're going to have to put in to get where you want to go. So that's Jupyter on AWS. Yeah?
Do you think there are other domain-specific, like the game-specific reasons, game mechanics, that we could be seeing that low result?
I mean, it could be that the matchmaker is really good. And so that for any given pairing, it's really a 50-50 shot as to who's going to win. If the matchmaking is perfect, that's what you would expect to see.
Okay. Would that be hard to fight against?
Pardon?
Would that be hard for us to apply techniques to fight against and build a more predictive system when the matchmaker is trying to draw that down to 0.5?
It's hard to say. Certainly, there's sort of the notion of the meta. At a certain point, team compositions are prescribed by how the game is played at high levels of play. Mm-hmm. There might be ways of working around it, but we would have to be using a different data set gathered in a different way.
Okay. System where each team alternates picking one hero prevents from getting wildly imbalanced teams in the ranked system anyway.
Yeah, exactly.
Okay. Thank you.
So with that aside, let's talk about what Jupyter looks like on the other platforms.
All right, so I'm going to jump in and start with Google's cloud platform. Different UI and yet inspired or similar. Here we've got the notebooks section. So we're going to start by finding a notebook. In this case, we have to specifically enable the notebook API. And we're going to select Python because, Python is what we're used to. Now, part of the reason we had to specifically enable that API is because this is in beta, but this is Google's beta, so it's fully featured, fully functional, and it could be in beta for the next 10 years, who knows. How long was Gmail in beta?
I don't know, something double digits, I believe.
Yeah, so Google's definition of beta. All right, it's gonna take a minute to provision the instance. This is go get a cup of coffee kind of time waiting, not go get lunch. And that's pretty typical across all the platforms. Once you have the instance, you can then do something with it. We're gonna run the instance and Right now, we're in the Jupyter UI, which should look exactly the same as what you'd see on AWS or Microsoft's Azure, because Jupyter is Jupyter once you've gotten it stood up on that platform. All right, I'll run through the same steps on Microsoft's Azure. So again, similar UI, but yet slightly different. They have a notebook section. So in this case, code with a Python SDK. So we'll start now. Prompt us for a file name, DotA2 win classifier. Once we've saved the file, we've got the basis for our notebook, and we can simply run it and upload the file as we have with the other ones. Again, by the time we get to this point, Jupyter is Jupyter.
So with that discussion of how similar the various platforms are for your initial exploration, we wanted to turn towards how they set themselves apart and what might make you want to pick one over another. So we're going to start that discussion by looking at AWS. The first thing I want to talk about with AWS is Mechanical Turk, and it really helps with these two stages of the pipeline in particular, data validation and data preparation. So this testimonial from the Allen Institute for Artificial Intelligence, I think really encapsulates what Mechanical Turk is great at for machine learning problems, and that's labeling training data. So you've got, in our case, we have a big data set that someone already curated for us, but it's easy to imagine a project where you want to have some sort of classifier that can label whether or not an image contains a certain object or property. But to get that training set to work with, you're going to have your engineers sit down with piles and piles and piles of images and label them one at a time by hand. Well, you can instead trade money for your engineer's time and have other people label those images for you using Mechanical Turk as a service. So the notion is that it's, if you're unfamiliar entirely, it's sort of a matchmaking service. It marries people that have relatively low complexity jobs with folks that are willing to do tasks for a certain amount of money per part. And for machine learning, for classifying instances to get a good training set, or for cleaning up data, it's sort of ideal. And AWS has the added benefit, you could always use Mechanical Turk and then take your data to another platform, of course, but AWS has the advantage that, well, it's already up there in an S3 bucket or whatever, you can just access it. You don't have to take it back out and do those extra steps. The other place where AWS really sets itself apart, I feel, is in its algorithm marketplace. So if you're done with your Jupyter notebook, you're looking to move to a more production level system for your machine learning stuff. One thing you could do is you could take that Python that you wrote or whatever it ends up being, as part of that Jupyter notebook, encapsulate it in a Lambda and use that as a machine learning function. Alternatively, if you have a sense of, well, these kinds of techniques are good, and so I just want to use the best-in-class version of that or something tuned to my thing, you can look and see if someone has already provided that as an algorithm for machine learning on AWS. So you would go to a search box like this and say, well, I want to see if there are decision trees, because that's what I used in my Jupyter notebook. You see, well, there are a number of decision trees. In fact, there's a wrapper around the scikit-learn decision tree that we used exactly. So I'm going to select that. And what I get is a description of what the algorithm actually is. In this case, it says that the Amazon engineers put a wrapper around an open source library and provided it for experimentation and testing purposes. You get a sense of what kinds of problems the algorithm is good at solving. They say that right there. So regression, classification, and so on. And then you say, okay, well, this is the thing I want to use. Let's go forward with that. And you're presented with a bevy of pricing options at that point. So you could, sometimes they charge just as a sort of single one-off use. I'd like to buy this algorithm for my future consumption. Sometimes it's more on a per compute use. I want to use this kind of computing resource for this duration for this algorithm. But it's effectively, how do I want to use the algorithm? Is this appropriate for my task? Can I trade sort of my own money for my development time, kind of a thing. Once you've selected the algorithm for your use, you set it up to train. There are a lot of options here. First, where do you want the trained model to live? Where do you want the training to happen? So since we're in US East is the region that's sort of closest to us, so that's what we end up selecting. We ask for a hyperparameter tuning job to sort of tune the algorithm beyond its initial configuration to pick the best set of parameters for the algorithm. And we're given a lot of options in terms of how much compute resource do we want the node that it's executed on to have? Do we want to sort of keep the resulting model in a warm start state so that we don't have to spin up a resource and wait 30, 60, 90 seconds on the first query, and instead it's a much faster response all the time? That sort of thing. So that the breadth of configuration options that Amazon gives you is another great advantage if you're effectively, if you're a power user and can select the most effective options for your particular problem. Once we've got the data, the training job ready to go, we have to point it at a test set, training set, excuse me. And for me, this is where I made a mistake and had forgotten that, oh yeah, it's gonna have to have somewhere to access the data from that isn't my notebook. So I had to go out of Flow, construct my S3 bucket, load the data up there, and then come back to this, come back through this whole dialogue to point my training at the appropriate thing. There wasn't a nice way of creating the bucket right here where I ended up wanting it, which was unfortunate, but not a huge inconvenience. After running the training, a model is emitted again to another S3 bucket, and then you can construct an endpoint using the model, using the dashboard here.
Okay, so I'll go through the same process and we'll talk about what differentiates Google Cloud, where it stands out from its competitors. It really shines in the machine learning space, and more specifically with its AutoML capabilities. Now, I'm not going to go too deep on this topic, but the gist of AutoML is that you can give a data set to this AutoML engine. It will then train, deploy, serve. It will also evaluate a model produced from an algorithm. It will do some of the hyperparameter tuning, and then we'll also, and this is what sets AutoML apart from hyperparameter tuning. It will repeat that process for other algorithms also, or it can. That's an option. There are a few presenters talking later today. I see Silvana is talking. Calvin, our hero Calvin, and Shane Milton are talking about AutoML later over the next 2 days. So for more information on that, they will have more specific presentations. But for our purposes right now, it's a slightly more advanced version of hyperparameter tuning where you can also tune multiple algorithms and get a best overall. Google's cloud platform makes that easier than the others.
Oh, and by the way, I appreciate the plug of my talk. Thanks.
No problem. In addition, it lets you do some more specific selection, whether your AutoML generation is for vision or language or something more structured. And I've heard, although I have not personally tried this myself, that it's OCR, optical character recognition, so taking an image and extracting generally text from it, is just absolutely superb and better than its competitors by quite a good margin. So I wanted to point that out here too. Let's step through real quick a similar process to what Jordan did with AWS. So Google Cloud here. Making a pipeline is still relatively simple. So you can see that we already have put our CSV file in a bucket. We generated the bucket, we put it in there similar to what we did on AWS. We can then make a new training job to build a model from that CSV. And here it's very simple. You can see here that it's asking for what split of the input data, so the composite CSV file we want to use for validation purposes, and then it's also asking if we want to further split it for testing purposes. The nuance between those two I'll actually talk more about later, but for now just know you can split your input data twice if you want. Sometimes you only want to split it once. You create your training job. It's all very straightforward. The defaults are very useful. And this is an interesting thing that Google Cloud has chosen to do, very specifically chosen to do, is limit the algorithms that you can select from. Initially, sort of our intuition was that this was not a great thing. The selection of algorithms is considerably smaller than what AWS offers. And we thought, well, fewer options is not as good. It is just clearly not as good. But when we looked at the options, what Google has actually done is made sure that they are sort of best in class. So you might have multiple algorithms that are all very similar and tuned to do slightly different things. Google has selected one that is best overall for that class of algorithms and made it available. And then the best of another class of algorithms, and so on and so on. So it's actually a rather interesting decision, a deliberate decision to limit the configuration space and sort of help narrow your focus. So if you're just getting started, you have, well, frankly, fewer ways to get it wrong, and you have sort of a better opportunity to explore and get a better result faster. Again, if you are a true power user and you need a really finely tuned algorithm, AWS might be a better option, but we'll go into more detail with that later.
You could always implement custom code here as well, of course.
True, but for a starting point, right?
Yeah.
Beginner, yeah, you're right. Then you create you provision your resources, and similarly, they have very limited configuration space of the scaling tiers too. I think it's basic, medium, and super or something. There's like 3 options, whereas AWS, you saw that long scrolling list that had probably a dozen, if not more, options in it. So again, they have very deliberately chosen to limit the configuration space, which streamlines it in some ways. Once you've provisioned your instance and your training job runs, you then get your output, and the model is saved to some location. You can see that it's got the output, it's got the input, it's all very easy to understand. And this is all machinable too. There's an API behind it if you need to interact with it in a programmatic way. The model is saved, so you can then use it and consume it later. Later being now. To consume that model, we can wrap it in an endpoint. It's as simple as giving it a name, a region, and then clicking create. And you can select some of the specifics for the resources that it's going to run on, but the defaults are fine too. You can see that at the bottom we've selected which model we're going to be operating off of. And this is something really handy. Google Cloud provides sample request code. So in this case, it's got G-Cloud, Python, and Java. Now, we're using Python for all of our examples, so we've left it here. But it's as simple as grabbing that code, that sample, and then putting it into your app or whatever your system is and running it to make sure that everything is running correctly. You hand it the features to predict, and it will return you your labels, and you can sort of close that loop real quick. It's nice and handy. All right, next up is Microsoft's Azure. It really shines in the data preparation and machine learning steps. And because when you are creating your data set, you can tell it, this is a delimited file, you can tell it a little bit more information about the file. So instead of just being a blob, it knows it's delimited. It knows that it's delimited by a comma. It knows whether it has headers or not, and it gives you a nice little preview. So you have a little bit more confidence earlier in the process that you are going to be able to interpret this file, and Azure is a little more powerful because it knows a little bit more, understands a little bit more about the format. In addition, you can select the label column. Since we're only predicting one thing, we only have one label. Everything else is implicitly a feature. But you can select the column here, and its visual pipeline editor will know now, again, more about the contents of the file and the structure of it. There are lots of choices. So this is, I think in terms of choices, Jordan, correct me, my memory is a little fuzzy. This is in between AWS and Google's number of algorithms to choose from?
I think that's fair, yes.
Okay, so you've got a middle ground between the two. You have lots of algorithms with different classes. Some are better for some things. So requiring some knowledge. Was that a question? I got a ping on Zoom.
So we've got 5 minutes left.
5 minutes left, okay. All right, excellent, we're right on track. So this is really the core of the visual pipeline editor here. This is all drag and drop in the Azure interface. You can see that we started by dragging over the data source. We then gave it a summarized data node, so similar to what we saw in Jupyter, we can summarize the data and make sure it looks like what we're expecting. We can then split the data, and can you see my cursor here? Yep, okay. So the first split here is for our data that we're using to tune. So we've decided to use the decision forest regression. Again, this is not AutoML, this is hyperparameter tuning. So this algorithm plus the main part of the data is what's being used to tune. What it was split out, we're going to split again and use part of that to evaluate the tuning. That's what helps us know if the tuning is effective and whether we need to move in certain ways or not. Again, all automatically done by Azure. And then the remainder of the data, this is where the two splits give you 3 sets of data. is what we're going to use to evaluate the model. We don't want to use the data that we used for tuning to also evaluate and score the model at the end to avoid overfitting, basically. One of the big benefits to this visual pipeline construction is that it maps very well to the pipeline model that we saw before. You have ingestion, preparation, learning, and evaluation. This makes it really easy for people who aren't super comfortable with the code. Maybe you have data scientists rather than software developers to get started with this too, and to tinker with this, get them up and running faster, basically. It also implements a lot of the evaluation metrics in a more visual fashion, so you can see various graphs of how these things are working. Also, the metrics down here are easily consumable, and these are pretty common standard metrics: accuracy, precision, recall, F1 score, and so on. And then you can see down in the bottom right your type 1 and type 2 errors, as well as your correct predictions. Deployment is actually rather simple too. You simply set up a published pipeline, you give it an endpoint name, you select your pipeline that you're publishing, and you click publish, and you're good to go. It's out there and accessible.
So just to wrap things up, there we are. So there are more than the three providers that we talked about today in terms of machine learning in the cloud. But I think that even without having looked at them super deeply, I think this is still relatively true. No decision you make in terms of platform provider is going to limit what you can actually accomplish with machine learning in the cloud. It may make certain steps more difficult or more expensive, but at the end of the day, you're still going to be able to achieve similar outcomes no matter what provider you pick. So if you find yourself already working in the cloud in some capacity, which likely you do, I would recommend that wherever you happen to be today, that's probably where you ought to stay if you have one preferred provider, because the things that set the offerings apart that we looked at today, at the very least, they're nice, but they're not so nice as to dictate a change, a radical change in terms of where you do work. Now, if you haven't made a decision, or you find yourself using all of the clouds fairly equally, then you have a more meaningful decision to make. And I think that the differentiators we looked at are a good way of deciding, well, I'm going to use this service over another. So just to sort of go over that again in very brief detail, or very briefly, Azure's visual editor is nice if you have people who aren't programmers that are doing a lot of the machine learning for you, because they don't have to dig into the code to go from a data set to a working endpoint. AWS is great once you become a power user of machine learning, because you can really narrow in on exactly what it is you need in terms of hardware and minimize your cost. And Google's cloud has one of the stronger AutoML offerings, and its limited configuration space really focuses your attention, which we found very helpful. So with that, thank you all for attending and your attention. And I think we maybe have a minute or two to take questions if there are any.
Yeah, actually, if we want to move over into the breakout room,
Sure.
There's a few people in there right now, but there's going to be a breakout room where actually people can ask face-to-face questions. I didn't see any questions in the channel necessarily, so I think that would be a good place for folks who are here right now and want to ask Jordan and Robert both more questions in person. We've had a lot of good luck with people getting interaction through those rooms.
Great, we'll hop over there shortly then.
Real quick then, just in terms of closing, I want to put a URL up on the screen. So our slides are posted there if anyone's interested in them, as well as further reading links on a lot of the topics that we've covered. So I'll put that in Slack too. And
Perfect.
I just wanted to express to the attendees our thanks for giving everybody a little grace and understanding. There's been a lot of shifting in Calvin, you called that out. And so it's, it's been quite an experience. So I want to thank everybody for that, and just encourage them to keep that in mind as the other presenters continue throughout the day.
Yeah, thank you.
Thank you. Notable talks related to cloud ML. I see that Maria is talking about deploying ML pipelines. Stefana is talking about ML model deployment. And then, as I mentioned earlier, Calvin and Shane are focused on auto ML. And then Harnor, I hope I pronounced that right, is talking about an ML in 45 minutes. So there are some very relatable talks. I encourage you all to check out.